Every industry right now is chasing the same physical requirement, cramming more energy into smaller, lighter packages that last longer. But packing highly reactive chemistry into a tightly confined space generates a massive, unavoidable byproduct: heat. If that heat cannot escape a single cell, the internal temperature spikes until the chemistry breaks down and the cell ignites. That failure then spills into the next cell and the next in a chain reaction called thermal runaway. The ultimate ceiling on how much power we can put in a battery is dictated less by chemical engineering and more by how well we can physically manage that failure state. This gap of empty space is fire spacing. It acts as the primary defense, ensuring thermal energy from a burning cell dissipates before igniting its neighbor. While negligible on one cell, this gap multiplies across thousands, expanding the entire battery system's weight and footprint. This engineered void of empty space dictates the final geometry of a modern battery more than the physical cells it contains. Engineers are trapped in a physical trade-off. Maximizing power requires eliminating empty space, while guaranteeing safety requires expanding it. Finding the exact millimeter where thermal safety meets peak power density requires a calculation that accounts for hundreds of structural and chemical variables simultaneously. You cannot solve this through physical trial and error. Building prototypes just to watch them burn down is dangerous and financially unsustainable. This balance must be proven in the concept stage, the digital environment where you simulate the physics before a single physical part is manufactured. In this quiet, early phase, a product's physical constraints, its risk profile, and its ultimate character are locked into place. Nailing that balance requires the simultaneous calculation of thermal dynamics, spatial geometry, and raw material costs. The teams that solve this do not pick one idea and slowly refine it. They front-load their exploration. This means generating and comparing dozens of different architectural directions at the very start of the project. By overlaying thermal load data onto these different configurations, they can view the architecture from every possible angle and constraint before they commit to a single path. These teams succeed because they exhaustively find and eliminate failure points in the digital space long before physical reality takes over. Moving from the concept stage into manufacturing means crossing a permanent threshold. This is the tooling phase. You lock in global supply chains and cast steel molds based entirely on structural decisions measured in fractions of a millimeter. If a critical error in thermal spacing is discovered after these assembly lines are built, it results in a total logistical and financial catastrophe. Once the metal is cut, the design is no longer fluid. It has become an unyielding, expensive reality. Since the transition to tooling is irreversible, the exploration of these variables must happen early enough to allow for dozens of architectural pivots before hardware is produced. Depix design intelligence is built to make this rapid, front-loaded exploration possible for engineering teams. It enables teams to process the volume of data required to move into manufacturing with a design where every clearance and thermal tolerance has been validated. A decision is cheap as a sketch, but brutal once tooled. To win, teams must see every angle and draw the irreversible line on purpose.